Thank you, David, for introduction. And I also like to thank Sophion and for giving me an opportunity to give presentation today. I'd like to talk about TPC3 channel. And this work is really now hot from the oven. So two-pore sodium channel, TPC. So this is not TRPC, TPC. And as you know, voltage-dependent potassium channel has 4 repeats. And this one forms one functioning unit, as you know. And the prokaryotic voltage-gated sodium channel has only 1 repeat. And the tetramer 4 subunit forms one functioning unit. And there is another class of sodium channel, which is called two-pore sodium channel. Actually, 2 repeats, two domains. So that's why to form one functioning unit, 2 subunits needs to be combined. So we are working on this channel. And when we expressed Xenopus tropicalis TPC3 in Xenopus laevis oocyte, and when we applied long depolarization pulse, this is 20 seconds. So the current looks like this. At the beginning, there is almost no inward current. However, it increases very slowly and gradually. And by going back to the resting potential for a while, and if we apply the next pulse, so then the activation is relatively rapid. And however, if we hold at holding potential for more than 10 minutes, so then the channel goes back to the original state. And inward current is activated only very slowly. So that's why it seems there is a sort of induction mechanism by sustained depolarization. So and we really want to know the molecular mechanism of this induction by sustained depolarization. And in TPC family, there are 3 members, TPC 1, 2, and 3. And TPC 1 and 2 have already been studied very intensively. And it is expressed in organelles like lysosome and endosome. And in 2009, it was reported to be calcium channel, organella calcium channel activated by NADP. And later on in 2012, it was reported to permeate sodium ion also and is activated by phosphoinositide, PI35P2. And in any case, it is a very important ion channel for the lysosomal function. And as I mentioned, it is activated, this is story of TPC2, and it is activated by 3,5P2. And this is before, in low concentration, and this is in high concentration. And as you see, there is an increase in the current amplitude. However, if we compare the normalized current here, there is almost no shift of the voltage dependence. No shift of the voltage dependence before and after application of 3,5P2. And please remember this point. And this is TPC3. And in contrast to TPC1 and 2, TPC3 is expressed in both organella membranes and also external surface or plasma membrane. Plasma membrane also. And it is reported not to be activated by phosphoinositide 4,5P2 or 3,5P2. And this is a recording of the voltage-gated sodium channel, and it activates very rapidly and inactivates. This is 10 milliseconds. And in contrast, TPC3 channel shows sustained slow activation, and it doesn't inactivate. The activation is sustained. So that's why once this channel is activated, then it has a very strong effect of depolarizing effect. And as a physiological role of TPC3, one thing is known in starfish egg. So the strong depolarization evoked by TPC3 upon fertilization serves to protect duplicated fertilization. So this is one example of the physiological role. As to the structure, so this is a prokaryotic sodium channel, one repeat type, and it forms symmetric tetramer. And the TPC1 structure was solved by cryo-EM approach last year. And as I mentioned, there are two domains and two subunits combined together to form this functioning unit. And the second domain is more critical for the voltage sensing. And as I show later, first domain is critical for the PI binding. So in any case, this is a very starting point of our observation, and we wanted to approach the molecular mechanism. And from here, I'd like to show our data. So first of all, as I mentioned, there is an induction of activation by sustained depolarization. And by applying set of short step pulses before induction and after induction, we compare the GB relationship. And this is before induction, and this is after induction. So there is a significant shift, hyperpolarization shift of the GB relationship. And this is under the base of induction, because at 50 millivolt, the GB curve shifts from here to here. So that's why this enables induction of the inward current. And the presence of this shift is in remarkable contrast with the case of TPC1, which didn't show any shift. And Professor Okamura's group in Osaka University used fluorescent sensor which detect 3,4P2. And they recorded 3,4P2 level upon depolarization. And in this case, no molecule other than the sensor is expressed, no ion channel at all. So, and they found upon long depolarization, there is a gradual increase in 3,4P2 level. So it seems as if this is produced by endogenous voltage sensing phosphatase. And also, as I mentioned, in the case of TPC3, 4,5P2 and 3,5P2 are known not to be effective to activate this channel. So that's why we saw this molecule might be a key molecule to activate TPC3. So there is a very convenient molecule to manipulate the PI level, voltage sensing phosphatase. So this is phototransfer protein, and the phosphatase activity, which degrades PIP3 to PIP to PIP, is regulated by depolarization. Upon depolarization, this enzymatic activity happens. So we co-expressed this voltage sensing phosphatase with TPC3. And then upon depolarization, the activation was observed very rapidly, and it showed also decline of the current. And this rapid activation and decline could be explained by the first step of the catalysis and the second step. So PIP2 is produced, and then it is catalyzed to PIP. So maybe one of these could be critical. And also, there is one interesting mutant which doesn't change the first step, but hampers the second step. And in this case, the activation was a bit slower, and more remarkably, the declining phase was far slower. So that's why, again, it's supposed maybe these could be a key molecule. And using fluorescent sensor for 3,4P2 and 4,5P2, we also measure the time course change of time course of these PIPs. And in this case, we co-expressed VSP molecule. So, and for example, at plus 50 millivolt, there is a fast activation and also rapid decline of the current, as I mentioned before. And correlating with this kinetics, an increase in the 3,4P2 level and the decline was observed. And at very high potential, as the breakdown goes rapidly, there was not too much current and also not too much 3,4P2. And in contrast, 4,5P2 sensor detected these changes. So this kinetics is very different from the change of the current. So that's why, again, we think, so maybe this is a key molecule. And also, we measure the PI3,4P2 level and the 4,5P2 level in the absence of co-expressed VSP. So in this case, as I mentioned, by depolarization, inward current is produced very slowly, and correlating with this change, 3,4P2 level increased very slowly. And there was almost no change for 4,5P2. So, and maybe this is achieved by low level of endogenous VSP. So low level of endogenous VSP produces 3,4P2 very slowly. So that's why inward current is induced slowly, and this is the time course of the 3,4P2 change. And to show directly these PI-P2 is critical for the induction, we did injection of PI while we are doing 2 electrode voltage clamp. In the course of recording, we did injection. And as you see here, there are 2 plots. One is current amplitude and activation time course upon depolarization. When we injected 3,4P2, there was an increase in the current amplitude and the acceleration of the voltage-dependent activation. So looks 3,4P2 is important. And this is summarized data, and this is activation kinetics, and this is normalized current amplitude. In both cases, 3,4P2 gave most clear change. And please remember, 3,5P2 did not show any effect here, only 3,4P2. However, we did excite inside out patch recording. And then applied PIs directly to the excite inside of the membrane. And in this case, by applying 3,4P2, there was sorry, I made a mistake. Sorry. Yes, and we did an excite patch experiment and applied PIPs directly to the inside of the membrane. And as shown here, PIP3 was not effective at all. 4,5P2 not. 3,4P2 was effective as we expected. And surprisingly, 3,5P2 was also effective. So this is in contrast to the result in the whole cell injection experiment. So there could be some mechanism to prevent 3,5P2 in the whole cell experiment. For example, 3,5P2 is known to be localized preferentially to the organelle membrane. So that kind of prevention mechanism exists in 3,5P2. And in any case, on the TPC3 channel expressed in the plasma membrane, 3,4P2 is a most critical molecule for the activation. So from here, I'd like to show some data about the structural background. First, identification of the PIP2 binding site. And the TPC1 structure was solved by cryo-EM approach with 3,5P2, which is docked here. From here, we constructed a homology structure model of Xenopas tropicalis TPC3 with 3,4P2. So in this case, 3,4P2. And this is a putative binding site, which is formed by, after S6, 4,5 linker, S4, S5 linker, and S3 domain. So, and this pocket. And there are obviously many positively charged amino acid residues, which looks to be critical for the binding of the phosphate. And from here, I'd like to show two important mutants. One is R187, which is located here. And this one looks to be critical for the binding of phosphate at the 3 positions. And in this mutant case, before and after induction, there was almost no change of the current. It is depicted in blue here. You see there is almost no change. And also I'd like to highlight one more mutation, R297. So this is pointing to the opposite side of the PIP2. So that's why this doesn't contribute to the binding of PIP2. However, in this case again, the induction was much smaller than the wild type. So that's why this one looks to be also critical. And this is a summary slide of various mutations we performed. And for the PIP2 binding, these positively charged amino acid residues in S3 and 4,5 linker are very critical for the binding. So, and yes, so the loss of the shift of the GB relationship proves these are critical. And also, in the case of 187Q mutation, which is most remarkable mutation, and if we apply 3,4P2 to the whole cell, the effect of the injection was very limited. So that's why this 187 destroys the binding site for the 3,4P2 and stops the induction. And there is one more region which is critical for the binding. This is N-terminus cytoplasmic region. And there is NRN sequence, NRN for TPC3. And among these 3, we found this one is really critical for the docking of the PIP2 because all these mutations decrease the GB shift remarkably. And this R53 is facing to the opposite side to the phosphate of C4 position and is not too critical. So this one looks to be most critical. And in the case of TPC1, which docks 3,5P2, so this position corresponding to this position is lysine 87. And this is really critical for the docking of the phosphate at the C5 position. And finally, I'd like to introduce a result about the coupling mechanism. So as I mentioned, TPC1 can be activated by 3,5P2. However, there is no GB shift. In contrast, in the case of TPC3, there is GB shift upon induction by a sustained depolarization pulse. So that's why it seems there is a coupling mechanism between 3,4P2 effect and the voltage-dependent gating. So as I mentioned, in domain 1 is a critical site for docking 3,4P2, and domain 2 is more critical for the voltage sensing. This is said by the mutagenesis analysis of the positively charged amino acid residues in the S4 region in domain 1 and domain 2. Domain 2 is more critical. So what's the coupling mechanism here? And I think you remember 187, which is critical for the PIP2 docking, and I said another mutation, 297, which is not pointing to the PIP2 direction. So this one is located in S6 transmembrane domain of domain 1. And there is domain 2 S6 region here, and there is one critical amino acid here. So again, this is domain 1 S6. This is domain 2 S6. And this is positively charged arginine, and this is negatively charged glutamate. And this electrostatic interaction is critical for the coupling because mutagenesis destroys the induction, And the charge swapping mutation, plus charge here, minus charge here, restore the induction mechanism. So that's why for the coupling of the PIP2 binding and the voltage-dependent gating, this electrostatic interaction looks to be critical. So this is a summary slide. Upon sustained depolarization, so by the low level of endogenous voltage sensing phosphatase, PI34P2 is produced. And that PIP2 binds to the domain 1 region. And there are some critical amino acid residues like R187 and N54. And when this PI34P2 is docked to domain 1 by the electrostatic interaction between S6 of domain 1 and S6 of domain 2, there is a coupling to the voltage-dependent gating, which induces the shift of the GB relationship. And we believe this is a mechanism of the induction of TP53 channel by sustained depolarization. And I'd like to acknowledge Professors Fujiyoshi, Okamura, and Isakov for providing us with these precious materials. And also, all this work I introduced today was done by Dr. Takushi Shimomura in my lab. All data was obtained by him. So I appreciate if you could remember his face and name. Thank you very much for your attention.
It's a great talk, thank you. I can't get my head around this amazing specificity in phosphoinositide action, yeah? So you showed that at 10 micromole, PI45P2 doesn't do anything, yeah? But at the plasma membrane, we have 100-fold or more higher concentration of PI45P2 than 3,4P2. So in a real situation of an intact plasma membrane, would you not expect that your binding site will still be occupied by PI45P2, and how do they compete? So can you comment on this?
I think 4,5P2 cannot bind to this molecule.
At all, yeah?
At all, yes. Because in both injection experiment and the excite patch experiment, 4,5P2 was not effective. So,
did you go higher risk concentration to 100 micromole, for instance?
I'm
May
not
have
sure
missed that.
how high it is, but we believe it is sufficiently high. So this is just exactly exposed to the inside of the membrane. And the 4,5P2 is not effective at all. So that's why even if there is a very high concentration 4,5P2 beneath the membrane, I think it will not bother or compete with 3,4P2.
Hi, Hiro. Very nice talk. So what's really intriguing about the sodium channel is it's got these two domains. Each domain's got a voltage sensor, but it only seems to be using one of the voltage sensors in a conventional way. And so what I was thinking is when PIP2 binds to domain 1, could it be that it's pushing that voltage sensor so that it's now acting like a voltage sensor, and that now coupled to the other voltage sensor causes the shift in the GV? Is that different from what you're arguing for? It sounds like you're arguing for the binding of PIP2 facilitates the movement of the voltage sensor in domain 2. Is that right?
Yes, yes.
So is there a way to discriminate between these two kind of mechanisms?
Yeah, and it's very hard to discriminate, but what we have is by the mutagenesis of the positively charged amino acid residues in S4 of domain 1, there is almost no effect on the voltage-dependent gating. And another result we have is if we do voltage current flowmetry by leveling the S4 region of domain 1, there is almost no change. So that's why we think it is not too mobile. And only the voltage sensor in domain 2 is mobile, and it regulates the voltage-dependent activation, and facilitation by PIP2 is effective to make it easier to activate this channel.
But it's a curious thing, right? So it's as if this channel's evolved, even though it's got a voltage sensor, but that voltage sensor is now a binding site for PIP2, which is kind of surprising. I don't know if there's any other sodium channel that might work like that.
Yeah, it is surprising. Yes.
Yeah, it's very
It
nice.
is very asymmetrical, yeah.